All right, Honors Chem, we are going to learn a little bit more about sublimation and then go and talk about phase diagrams today. I'm going to just show you how to read them. And we will revisit phase diagrams a little bit later as well, because I feel like the videos for today's lessons are already long enough. So we're going to keep it as short as we can. So I want to define sublimation, okay? So sublimation is basically if we take something that is in the liquid phase and we take that something and it goes directly to the gas phase without passing through the liquid phase. So a change directly, a phase change. Directly from the solid phase to the gas phase without going through the liquid phase. Okay, so we don't ever see the liquid phase at all when something sublimes. Okay, so name a couple of things that sublime. You might have to do a little bit of research on this. Take a minute, pause the video. You can Google it if you want. We all know dry ice sublimes. We've all probably seen dry ice or played with dry ice. Dry ice is just carbon dioxide that's in the solid phase, and it goes directly to the gas phase. That's why it's called dry ice, because we never see the liquid phase. Can you guys think of something else that sublimes? Iodine will sublime. So iodine will go from the gas, or sublime, it goes straight from the solid to iodine gas. Okay, and another thing, how many of you guys have ever, it's kind of an old-fashioned thing, how many of you guys have ever heard of or seen mothballs? They're made up of naphthalene. Now that's naphthalene. It's kind of a long word, naphthalene, but that mothballs are these solid kind of balls. They're not kind of sticky, and they just evaporate into the air. So if you ever had an old-fashioned trunk that has linen or wool or something in it that moths will actually eat, a lot of people will put mothballs or naphthalene balls in there to kill the larvae of the moths. Okay, so doing sublimation is extremely endothermic. It takes a lot of heat. It takes a lot of heat energy to go from the solid state to the gas state. Okay, so when we talk about this, we're going to, in the next day or two, we're going to start talking about the heat that it takes to do this. And those are heats of fusion and heats of vaporization. And we'll define those in a minute. Liquefaction. Now, liquefaction has a totally different term for geology as it does chemistry. So geology is where the ground acts like a liquid in an earthquake. Chemistry, liquefaction is the process of liquefying a solid or a gas. The process of liquefying a solid or a gas. Okay, so we're going to define also, this is going to be a bunch of definitions. We're going to define critical temperature. Now, you're like, what could be critical? Now, critical temperature, we abbreviate it T sub C, is the temperature above oh my gosh, I can't write. The temperature above which no amount of pressure will liquefy a gas. Okay, so if I want a gas to become liquid, one of the easiest ways to do it is to pressurize it. We do that a lot, especially with propane. If you've ever grilled on a propane tank or a propane grill, you know that the propane in that tank is liquid because we can fit a lot more liquid in a tank than we can in the gas state. So we pressurize those tanks so that it becomes liquid so that we can actually put a lot more propane in there and it will last longer. Okay? Critical pressure. This is the pressure. And we will define this as P sub C sometimes. This is the pressure that is required at the critical temperature to liquefy a gas. So at the critical temperature, we can still liquefy it, and the critical pressure is the pressure that is needed to liquefy that gas. But once we get above that temperature, no amount of pressure will liquefy the gas. We will have what is called a superheated fluid at that point. Okay, so let's think about this. Which molecules are going to have higher attractive forces? Those with a high critical temperature or those with a low critical temperature? If I have attractive forces that are really high, I'm going to have a very high critical temperature in order to break those apart and make them a gas. So I am going to have high critical temperatures with high attractive forces. If I have low attractive forces, it's not going to take me a lot of energy, therefore kinetic energy, to get to a critical temperature. Okay, so here we go. We're going to put all these ideas of sublimation, liquefaction, critical temperature, and critical pressure in reading phase diagrams. So phase diagrams are really important, especially in chemical engineering. You will use them a lot if you ever become a chemical engineer. Okay, there are two variables that we can use to control the phase of a substance. Okay, we've talked about them before. We can use temperature. We can raise or lower the temperature. Like water, we can freeze it. We can make it water vapor just by raising or lowering the temperature. So we can use temperature. We can also use pressure. If I raise the pressure, I make it a lot harder for that water to boil. If I lower the pressure, I can even boil water at room temperature. So I can change the pressure as well to change the phases of a substance. Okay, so we use these two variables. They have an opposite effect on a substance. For example, a temperature increase causes more liquid to vaporize, but an increase in pressure causes more vapor to condense. Okay, so they're inversely related. A phase diagram is a graph of the pressure, and we always put the pressure on the y-axis, and the temperature, which we always put on the x-axis, which shows which phase a substance exists in during different conditions of temperature and pressure. Okay, now temperature is usually in Celsius, sometimes it is also in Kelvin. Pressure can be in atmospheres. So pressure can be in atmospheres, it can be in millimeters of mercury. I've seen it in pascals. I've also seen it in kilopascals, all kinds of stuff. Okay. Normally it's in atmospheres, but not always. Okay. We can vary the units of the pressure a lot. Okay. So this is the phase diagram for water. So notice that for my normal, and remember what normal means. Normal means at standard temp or standard pressure. Standard pressure is 1 atmosphere or 760 millimeters of mercury. Okay, so notice at my normal, at 1 atmosphere, my freezing point is indeed 0. And where I go from a solid to a liquid, at that pressure is 0. And if I go along that pressure for a higher temperature at 100 degrees, I do indeed hit the liquid to vapor line where things will boil. Okay, so we have a couple of different lines that are really important on this diagram. Okay, so this blue line right here from point A to point B is our vaporization line. So if we go from the liquid to the vapor side, we are vaporizing. If we go to the vapor to the liquid side, we are condensing. So that's the vapor / condensing line. If we go on this red line from A all the way up, this is our melting freezing line. So if I go from the solid to the liquid, I'm melting. If I go the other way along this red line, from the liquid to the solid, I am freezing. Now this yellow line down here, this is what we call our sublimation line. This is where we go from the solid to the vapor state. So if I go from the solid side to the vapor side, I am subliming. If I go from the vapor side to the solid side, I am depositioning. Okay, or depositing, depending on how you want to pronounce that. Okay, so those are the 3 lines that are really, really important. Okay, so let's look at some of these points that are really also important. Important points on a phase diagram. We have our T sub m. This is our normal melting point. Now remember, normal means that we are at a pressure that is standard. So this is at standard pressure, which is equal to 760 millimeters of mercury, or 1 atmosphere, or 101.325 kilopascals. Okay? A standard pressure. TB, so right here, this would be our TM. That is our normal melting point. Okay? TB is our normal boiling point. Okay? Once again, we have to be at standard pressure to do that. So right here, this is our TB, our normal boiling point. And then last but not least, TC is our critical temperature. Now, if you recall from up top in our notes, our critical temperature is the temperature at which we can last liquefy the substance. So here at B, this is TC. This is our critical temperature. So the critical temperature at 373.99 degrees Celsius, we can still liquefy water if and only if we provide a pressure of 217.75 atmospheres or greater. If I don't have that pressure, water is going to be a vapor. But if I have that pressure or greater, it will be a liquid. Okay, above that temperature, no amount of pressure is going to liquefy water. It's going to be what we call a superheated fluid. Okay, so I just want to also show you this. A is what we call our triple point. Our triple point right here, this is point A. This is where all three phases exist at the same time. All three phases exist. So we have solid, we have liquid, and we have gas exist at the same time. So the triple point is the temperature and the pressure that we need for that substance for all three phases to exist at the same time. And yes, you can get all three phases existing at the same time. On our next round of modules, I will put a video showing a triple point demonstration of water. It's really cool to see water boiling and freezing and all of it going on at the same time. It's really cool. Anyway, so let's do some just looking at this diagram and how to read it. So we're going to create a scenario here. If I look at this diagram and I am going to look at, let's put this, I'm going to look at the 50 degrees Celsius mark, and I'm going to look also at the 2 atmosphere mark. Okay, so we're going to look at that mark. So here we've got 100 degrees and 0 degrees. So 50 degrees is going to be halfway in between here. And here we've got 1 atmosphere, and notice it goes really quickly to 217. So obviously this is not to scale. And a lot of times the pressure is not going to be to scale. It's going to be on a logarithmic scale. So I'm going to say that 2 atmospheres is probably going to be right about here. Okay? So if we look at this, we are definitely in the liquid zone. So at 50 degrees and 2 atmospheres of pressure, water will be in the liquid state. Okay? That's going to be in the liquid state. Now what happens if I reduce the pressure? If I reduce the pressure, I take that pressure down. So let's think. Our pressure is along the y-axis. So if I take that pressure down, I will go from the liquid to the vapor state. So as I go and take that pressure down, I will go from the liquid state to the gaseous state or the vapor state, which means I will vaporize. Okay, I will vaporize that water. Let's do another scenario. What if I start once again right back here at 50 degrees Celsius and 2 atmospheres? What if I decrease the temperature? Let's do another scenario. What if I take the temperature and I decrease the temperature? Now our temperature is along the x-axis. So if I decrease the temperature, I eventually will go from the liquid state to the solid state. Okay? So, and this is at constant pressure. And I should also say that this is at constant temperature. Okay? So if I go from, let's go back to this example, liquid to solid, I am freezing, right? That is what freezing is. Okay, third scenario. I'm going to start once again right here at 50 degrees and 2 atmospheres. What if I take the temperature and increase it at a constant pressure? So that would be going this way. So I would go from the liquid state to the vapor state. So I would take liquid and it would go to the gaseous or vapor state. So liquid to gas is vaporization, where I would vaporize. Okay, so that's how you read. Phase diagrams. We're going to do a couple phase diagrams in your homework, and we will do some more practice with phase diagrams in our next module. Hopefully you had, actually, let's see, triple point. It did go down here. Let's make sure we get the definition of triple point. So triple point is the point on the phase diagram that represents the temperature and pressure at which 3 phases, solid, liquid, and gas, all can coexist. All 6 phase changes, sublimation, deposition, freezing, melting, vaporizing, and condensing, are all happening at the same time. It's pretty cool. We'll see you later. Have a great day. Bye.